around height datums and geoid models and some of the considerations that need to go into preparing them. I'll just dive right into it. And I will just say, when I prepared this, I was kind of expecting to speak to decision makers and maybe people without a solid grounding in some of the technical considerations around this. So yeah, forgive me if some of it's a little bit elementary for some people in the room. There's obviously a lot of expertise here. So yeah, hopefully there'll be some productive discussions at the end. So yeah, there we go. What's going on? A little bit of a delay there. Okay. So yeah, I'm Jack McCubbine. Very grateful to be here this morning to talk to everybody. My background's really in applied mathematics, and my research passion is physical geodesy, geoids, and gravity field modeling. Over the past decade or so, I've computed 2 national scale geoid models, one for New Zealand and another for Australia, which have been officially adopted by government. And they're now being used as the kind of the official height reference surfaces. And over the past 5 years specifically, I've been working on really setting the future direction for geoid modeling and height datum development in Australia. And that's kind of involved transitioning from a legacy datum to one that's kind of more compatible with GPS and the way we work nowadays. The science behind the development of these models is a topic which is of great interest to me, and I'm particularly captivated by the kind of the societal and economic benefits that a precise geoid model can offer, and ready kind of access to heighting via GPS. I'm currently working at Geoscience Australia as a subject matter expert in gravimetry, which is often more of a science, the art than the science. And that's the kind of the science of measuring gravity very, very accurately. And I'm also kind of working in the space of modeling the gravity field. And yeah, today I'm going to be talking about height datums, and geoid modeling specifically. There we go. So yeah, to start, I'm going to provide some context and some common kind of definitions and concepts. So why is height important? I feel like that's probably one of the most foundational and important questions to answer. Well, being able to accurately determine heights to within at least a few centimeters is a critical capability for infrastructure planning, water management, engineering design, and community safety as well. Without precise knowledge of height, we can't confidently build houses above historic flood levels, design reliable drainage and sewerage systems, or construct roads and railways with the correct slope to ensure safe operation. Accurate height measurements allow us to understand where water will flow naturally, and how much land is at risk during floods, and how to deliver irrigation efficiently to agricultural fields. In the maritime world, knowing the underkill clearance of ships, the true sea level or tidal variations all depend on having a consistent and accurate height reference. And in mountainous regions, we need to know the absolute elevation of peaks for navigation, environmental planning, and even tourism and recreation planning. And at the heart of all of this sits geodesy and the use of height datums, which provide a common, rigorous reference surface from which all of these measurements can be made, tied together, and compared across time and space. Where without this geodetic framework, every height would just be a kind of a local guess in an absolute sense, and disconnected and prone to error. I guess in short, height is foundational because it underpins the systems and decisions that keep our infrastructure functioning, our communities safe, and our natural and built environments understood. So, I might be one too far ahead. There we go. So today, GNSS positioning data are readily available to anyone, from surveyors to scientists to everyday phone users. And by design, GNSS provides positions relative to the center of the Earth, defined within a global reference frame like ITRF, the International Terrestrial Reference Frame. And using this frame, we can guess positions as latitudes and express the positions as kind of latitudes and longitudes by calculating the angles those 3D coordinates make with planes that kind of pass through the Earth, so the equatorial plane or the prime meridian. For heights, GNSS relies on a mathematical surface called the ellipsoid, which is a very smooth, regular shape resembling a slightly squashed sphere, which approximates the shape of the Earth. This ellipsoid gives us what we call ellipsoidal heights, or kind of geometric heights, which are kind of unrelated to the gravity field. With the right GNSS equipment, such as geodetic grade receivers and enough time to collect and process data, we can achieve ellipsoidal height measurements accurate to within just a few centimeters. And this is just an incredible leap compared to the labor-intensive methods used in the past, like leveling, which makes, high precision geometric positioning accessible and very routine for many applications. So while GNSS gives us precise ellipsoidal heights, they're not the same as heights that we experience and use in practice, like heights above mean sea level. Converting GNSS heights to heights into physically meaningful heights, so ones tied to water flow and sea level and the landscape, requires the use of what's called a geoid model and careful integration with local height datums, which I'm going to drill into as we go through these slides. The distinction between geometric heights and physical heights is foundational to geodesy, and getting it right is just critical for many of the applications we just covered. Okay. So for heights to be physically meaningful, so be used to model water flow and all of those other applications, they need to be related to a gravity field. So more accurately, they need to correspond specifically to the amount of energy needed to move within the Earth's gravity field and overcome the kind of the local forces of gravity pulling us downwards. So for example, at the back of my house at home, I have a mountain, which I regularly try and climb to keep my fitness levels up. And it stands at about 887 meters tall, above sea level. If we lived on a perfect sphere and gravity were exactly 9.8 meters per second squared everywhere, I'd burn around 900 kilojoules of energy climbing to the top, which is about as much energy as a small cupcake. But gravity's not the same everywhere. For example, gravity varies by around 0.1% over the landmass of Australia. And here's a little gravity graphic kind of showing that gravity data coverage across the Australian landmass. Like any good geophysical network, it's based on relative data, which are tied off to a precise network of absolute measurements. And we have a set of locations where we've measured absolute gravity. That gives us a kind of a 9.8 meters per second squared type of number. They're shown there as the kind of the little markers, so the black squares, circles, and crosses. And the large majority of them have been measured with the A10 gravimeter shown there in the middle, the yellow thing. This is an instrument that drops a mass and measures how fast it falls with laser interferometry, and it can capture gravity very precisely down to about the 6th or 7th decimal place of kind of a meters per second squared type number. The benchmarks kind of act as a reference for more localized relative gravity surveys, which have typically been collected for mineral resource exploration purposes, which are shown as the smaller colored dots there, and represent the colors represent the kind of the graduating change in gravity across the continent. And these are typically collected with smaller, more portable instruments like the CG6 shown on the far right there. It's a network of observations that's been built up over many decades, stretching right back to the 1950s. And the technology has improved over time, but it's still very much the same. They're based on springs that stretch as gravity changes, and we infer that stretch, infer gravity from the kind of the stretch of that spring. So you'll notice quite a kind of a linear trend from north to south there. So most of those gravity variations are variations that reflect really the kind of the ellipsoidal shape of the Earth, which GNSS heights that typically kind of reference. At the equator, gravity is the weakest because we're furthest away from the Earth's center of mass. And as we move closer to the pole, we're about 20 kilometers closer to the geocenter, and gravity is stronger as a result. So yeah, on the whole, the ellipsoid captures a great deal of variation in the Earth's gravity field and is reasonably good as a result at predicting heights. But there are smaller scale variations too, which we need to consider for kind of meter down to that millimeter level variations in any geoid model or precise height. So once we have a gravity data set, we can dig a little bit deeper. So removing the effects of an ellipsoidal gravity field from what we measure gives a map similar to what we can see on the left there. The differences are known as gravity anomalies and are very small, around 0.01% of the kind of the nominal strength of gravity. They're typically caused by the irregular shape of the Earth, so mass density distributions where we have hills, we have more mass and a larger gravity value. Where there are valleys or voids beneath the surface, gravity is weaker, and as a result, we have negative gravity anomalies. So why is this all important? Well, you know, the classic kind of communicating vessels experiment shows that water typically settles to the same level. But over large distances, ellipsoidal heights don't really properly account for these variations in the Earth's natural gravity field. For accurate flood and irrigation mapping, we need heights that reference an irregular kind of undulating surface called the geoid. And this is a truly level surface in the Earth's gravity field. And it's computed from gravity anomalies, a bit like what you see there on the left. I'll get to that shortly. So globally, this kind of flat and level geoid surface deviates from the ellipsoid with a range of about 200 meters. And the difference between the geoid and the ellipsoid is often chosen to be 0 on average. Technically, you have infinitely many geoids, one on top of the other, but we tend to pick one that agrees most closely in an average sense with our reference ellipsoid. So GRS80 or any of those other ellipsoids that are kind of typically used alongside something like HightTRF. The largest feature is probably the Indian Ocean geoid low, which is clearly evident as that big blue pink splodge there. And this is the kind of the most prominent negative geoid anomaly on Earth. And it's thought to be caused by low mantle density beneath the Indian Ocean, as well as a subduction history and plate tectonics associated with the Indian plate's collision with the Eurasian. There's many features we could draw out here, and you know, it's the kind of map that just absolutely captivates me, but I won't get too hung up on that right now. Okay. So to actually determine heights above the geoid in practice, we really have two main options. The first is using the kind of classic spirit leveling approach, where height differences are measured incrementally, point to point, aligning the instrument along the local plumb line and closely following the shape of the geoid as we go. The height differences are then effectively kind of added up, often through a simple least squares adjustment, at the end to balance out errors and ensure that the final heights are consistent. And this gives us very precise physical heights, but it's slow and labor intensive, especially when covering large areas. And today we have much kind of better technology readily available in our mobile phones and, you know, survey grade GNSS equipment. So the other option, despite what I said earlier about the ellipsoidal heights, is using GNSS. So here we determine ellipsoidal geometric heights relative to the reference ellipsoid, and then we can subtract a geoid height from a geoid model to convert GNSS heights into physical heights. This is a method that's much faster, more cost effective, especially when covering broad regions, but it comes with a trade-off. It typically delivers lower precision compared to a well-executed leveling network. particularly because the accuracy depends not just on the GNSS measurements, but also the quality and the resolution of the geoid model being applied. Often those models are gridded up at 1 arc minute and typically around kind of 2 centimeters accurate. In my opinion, yeah, both approaches have their place, but understanding when to use each and how to integrate them effectively is central to modern geodetic practice, and I'm really hoping to draw that out with the slides that are to follow. So yeah, just to summarize, we really have 2 types of height. Geometric heights, which are simple, easy to use and capture, but are not necessarily physically meaningful and aren't going to predict how water will flow or really reflect, the height above a surface that is, corresponding to the amount of energy you need to use to navigate within it. Physical heights are the other option, but they're more complicated to measure. But they are physically meaningful, and they're vital to answer questions such as which way will water flow, what is at risk during a flood or sea level change, and how can we ensure the correct inclination of railways and roads. Okay. So there are a number of options when it comes to height datums, well, namely 3. We have leveling-based, model-based, and hybrid datums. So to provide users access to physically meaningful heights across the region, we need to establish a height datum first. These predominantly come in one of the 3 flavors, and generally the choice it reflects how measurements are going to be made, whether predominantly via GNSS or by using leveling methods or potentially both. So maybe a good place to start is, what is a height datum? It's difficult to define, and it's something Nick and I went back and forth on a lot over the years. But I think where we've landed is that it's a legally adopted, physically defined reference surface, such as a geoid, mean sea level plane, or other vertical control surface, coupled together with a specified height system. So orthometric, normal, and other nuances that I'll probably not go into much further.
Oh my God.
Yeah, but I'm happy to discuss this in more detail during any breaks. In practical terms, it kind of provides the single agreed upon 0 from which all vertical measurements within a jurisdiction are quoted, whether you're leveling a bridge, deck, or publishing flood maps, or every kind of elevation ultimately traces back to this kind of common surface. Data interoperability benefits. So because all users are using the same reference surface as a kind of a 0, the data sets that are collected by different users at different times and with different instruments interlock seamlessly. And this interoperability underpins national spatial data infrastructure. So that's going to allow engineers, scientists, and emergency planners to exchange elevation data without any hidden offsets or ad hoc transformations. So getting this right really does help future-proof any other kind of spatial mapping application. Longevity and stewardship. So yeah, a height datum is expected to remain stable for decades, often outliving the instruments that were used to realize it in the first place. And custodians therefore really need to monitor geophysical change, sea level rise, crustal motion, gravity field updates, and ideally really publish periodic realizations or corrections that keep the datum aligned with the physical reality, while also kind of preserving its historical compatibility. So by that, I mean going back out and re-leveling when ground surface motion happens with a leveling datum that's defined on physical infrastructure, or monitoring the gravity field with space missions like GRACE to make sure that you're capturing changes over time and keeping these things alive. The importance of this is that the long-term consistency really protects past investments and survey control, and ensures that kind of new and legacy data sets remain vertically coherent. and provides legal certainty for engineering design, land titling, and environmental regulation. So yeah, as I see it, there's really three major flavors of physical height datum, each with very distinct characteristics, field methods, and use cases, and really led by the intended measurement technique. So we have leveling-based datums. These are typically tied to tide gauge 0 points, carefully kind of propagated inland using spirit or digital leveling. And generally speaking, they achieve millimeter precision over very short distances, but it comes at the cost of very labor intensive methods, particularly when you're trying to cover very large areas or having dense networks. So these datums typically underpin dense urban engineering networks, floodplain control, and any legacy system where physical benchmarks and historic heights matter. GPS has only been around since the 90s, and this is probably the most common type of height datum, especially where they've been established points further in the past than that. So yeah, the second option there is gravimetric or model-based datums. So here the reference surface is defined by a gravimetric geoid or quasi-geoid, computed using gravity observations and digital elevation models. But it doesn't explicitly rely on tide gauge connections in its own right. So it's not necessarily directly linked to mean sea level. It comes with the benefit that the heights are accessed directly in the field using GNSS and a kind of a geoid lookup or interpolation of the model to the point that you're working at. And it enables very rapid heighting over large or sparsely kind of sparse areas, which really makes these kind of systems ideal for disaster response or remote mapping and kind of, modern GNSS based workflows. The third option is kind of a merging of the two things. So hybrid datums. And these blend gravimetric geoid models with existing leveled networks and can do things like absorb mean sea level offsets and create a geoid surface that preserves or incorporates any existing historic leveled heights. Hybrid systems let you transition from traditional leveling-based datums to GNSS as well, which kind of maintains that backwards compatibility and kind of helps ensure that old and new data sets can be used together seamlessly. So that's really the lay of the land. There's the three datum types, and yeah, they have different applications, but they're mostly led by the measurement technique. So how are leveling-based datums realized? Well, first we need to run a closed network of precision spirit level lines between permanent survey marks. So each mark, we record only the height difference to its neighbors, and the absolute numbers kind of come later. We then pick one or more tide gauge benchmarks, set them to 0 meters within the datum as a height, and run a least squares adjustment through all of the height differences. The single kind of computation propagates the mean sea level from the tide gauge through the entire network and gives us final orthometric heights for every mark. But it does rely on some physical infrastructure. So to keep a datum like this alive, we need to establish very stable monuments, deeply anchored brass discs or stainless steel rods, spaced around every 1 or 2 kilometers along primary routes. And the control hierarchy is typically kind of composed of both primary and secondary baselines, where primary first order lines tie in the tide gauge and national benchmarks to a very coarse network. And then secondary kind of second order lines densify the network, specifically kind of around towns and critical infrastructure. So this is going to rely on digital or optical levels to establish those height differences, and a rolling kind of re-leveling program that observes the network to catch any mark movement or subsidence or maybe motion from earthquakes or other sources that might disturb the physical location of those individual benchmarks. So in terms of kind of pros and cons, yeah, leveling is going to offer unmatched precision, specifically at local scales, about two millimeters times the square root of the distance in kilometers. So yeah, under 2 centimeters over 100 kilometers, which is just fantastic. It makes it ideal for engineering design and flood studies, and the physical marks provide a very clear legal traceability chain. The drawbacks, of course, is that it's incredibly labor intensive. A crew manages only, 2 kilometers of first order leveling per person a day. So 1,000-kilometer leveling campaign can take months, can take a very long time. And the other issue here is that any benchmark that moves breaks the chain until we come back and re-level. And systematic instrument biases can accumulate over long distances, which can produce the errors which can exceed 5 centimeters beyond about 250 kilometers. So yeah, I guess leveling gives us relative heights to tie GNSS points into the datum. We still need a geoid model. So yeah, another key issue with level datums is that they often reference a particular kind of local and time-locked estimate of mean sea level, and this can isolate them from other leveling derived height datums. From one place to another, the sea surface is not always on the same reference plane. It varies due to things like ocean currents, water temperature, salinity. So yeah, the mean sea level may be closer or further away from the kind of the equilibrium figure of the Earth, which is the geoid, depending on the geographic location. The zero elevation, as defined by one country or region, differs by up to 2 meters from the zero elevation defined by other countries, which can cause incompatibilities where these datums meet. And in fact, this is something we've seen in Australia. We have technically 2 datums, one for Tasmania and another for the mainland. And there's no real way to reconcile that without a kind of an understanding of those differences. So we have a map here of what's called that, that kind of those differences between the true mean sea surface and the geoid. And that's defined using satellite altimetry data. Where we have a gravimetric derived model and physical observations of where the sea surface sits, and we can see those variations. This actually has implications for the Australian height datum, which I'll get into. But yeah, there's a north-south tilt that's been introduced by these artifacts. Okay. So yeah, geoid model based height datums. So a geoid model based height datum defines the vertical reference surface entirely from the gravity field. So a geoid or quasi-geoid computed using national gravimetric data, a digital elevation model, and satellite gravity information. And there's often no explicit link to tide gauge observations. And you don't need them either to establish a model like this. In the field, GNSS equipment provides ellipsoidal heights, which are then converted to physically meaningful heights like orthometric or normal heights by referencing or using the geoid model to convert the ellipsoidal height measurements from the GNSS into an orthometric height by subtracting it. And this lets surveyors and engineers get vertical positions directly from a single GNSS observation without needing any leveling connections back to tide gauges or other benchmarks. So it's an approach that's especially powerful in large, sparsely surveyed regions where traditional leveling methods are just impractical or just cost too much money. And it supports very rapid GNSS-based workflows, which enables disaster response mapping and underpins national height systems that are often globally consistent and scalable. However, yeah, success hinges on the quality of the underlying geoid model, and the denser and more accurate the gravity and terrain data, the better. and we can use the data to define the separation surface between the geoid and the ellipsoid, and produce more precise final heights. In terms of kind of longevity and maintenance as well, one of the major advantages of a geoid model-based datum is their inherent resilience over time. Unlike level datums, which rely on physical benchmarks that can degrade or shift or be disturbed by ground motion, construction, or tectonic activity, the geoid itself is much more stable. So as an example, there was an earthquake in New Zealand in 2016, the Kaikoura earthquake, and there was up to 10 meters of vertical uplift. We forward modeled that into kind of gravity field equivalent changes, and we saw that the geoid model itself changed less than 10 mil. So they last a long time, and it's really a case of computing it once and having that in your back pocket for a couple of decades potentially. So yeah, overall, this reduces the need for kind of continuous field maintenance or re-leveling campaigns and makes the system more robust, even in regions where there's subsidence or uplift or earthquakes. Updates to the datum usually only require improving the underlying geoid model. So, for example, by incorporating new gravity data or even deriving it from INSAR-derived vertical land motion data, rather than physically restoring or remarking ground infrastructure. I guess in terms of kind of accuracy considerations, while kind of geoid model-based datums provide nationwide access to heights using GNSS, it's important to recognize their kind of practical accuracy limits. Even with a high-quality national geoid model, the geoid to ellipsoidal separation is typically only known to about 2 to 3 centimeters, and it's often even difficult to prove that that's the case. When we factor in the kind of real-world performance of GNSS, the achievable height accuracy in practice is generally only around 3 to 5 centimeters in an absolute sense. And, this is often more than sufficient for most large scale and mapping applications, but I guess it's important to set realistic expectations. The system won't replace precise spirit leveling for those kind of millimeter scale works, like, monitoring bridge deformation or capturing local subsidence. That said, in remote or sparsely surveyed regions, a geoid model-based height datum combined with GNSS offers a very practical way to establish new vertical control, even if local leveling is ultimately kind of required. So, for example, to set precise construction benchmarks or develop a local height network, the geoid and GNSS system provides a fairly reliable starting point that you can then level away from. So surveyors can use GNSS and the geoid model to fix an absolute height at a few key locations, from which they can then kind of run short leveling runs, high precision leveling loops. And this really just kind of reduces the cost and the need to transport leveling ties over very long distances, which will cut costs and improving efficiencies. So yeah, some kind of pluses and minuses to a datum that looks like this. So hybrid datums, option number 3. Hybrid datums combine the kind of the strengths of leveling based and geoid model based systems with several, I guess, different variations depending on really the intended purpose. So yeah, for example, one approach is to use GNSS observations combined with a geoid model to stabilize leveling network adjustments. And this works particularly well for work over very broad regions. So say networks exceeding 250 kilometers where accumulated leveling areas, which typically grow as sort of a 2 millimeters times the square root of the distance in kilometers, as I mentioned before. Where that can kind of reach several centimeters. So introducing a geoid model and GNSS height can really kind of bring a bit of stability to the whole process. You can introduce it as a loose constraint and help kind of suppress those long wavelength drifts and stabilize the leveling network without having to rerun or densify leveling kind of networks. Another approach is kind of to deliberately deform the geoid model. So, for example, by adding in a kind of a geometric correction layer so that a geoid model aligns better with existing leveling data where we have it. And I have a couple of examples of this in the Australian setting that I'll get into in a couple of slides' time. I suppose this kind of ensures that GNSS-derived heights are compatible with legacy datums and legacy heights, making it easier for a transition from, say, a traditional leveling network to kind of more modern GNSS workflows. A simpler variant, and one that I've seen published on quite a bit recently, is aligning a gravimetric geoid model with a local realization of mean sea level at tide gauges, which kind of ensures that the datum agrees with historical coastal benchmarks and has that kind of local specificity that you would you kind of like from a geoid model, which is perhaps being used for things like sea level rise monitoring. So yeah, while these kind of augmentations are highly beneficial for maintaining datum continuity and backwards compatibility, they come with a trade-off. Essentially, you're introducing a controlled amount of error or distortion into the geoid model to make it fit local requirements. So yeah, while the compatibility improves, you slightly compromise on the kind of the physical purity of the geoid model as a true gravitational reference surface. So yeah, really hybrid datums, they're a practical solution for jurisdictions that want the best of both worlds, the precision and efficiency of GNSS and geoid models, but without abandoning those kind of decades of investment in leveling based systems. So they're really trying to offer the best of both worlds by aligning a geoid model with existing data. So yeah, I'll wrap up by weighing the three height datum options side by side. So the first is the kind of the traditional leveling based datum. So this is a system that ties 0 to 1 or more tide gauges and propagates that surface inland with spirit or digital leveling. Its strength's really unmatched with local accuracy, millimeters over a few kilometers, which makes it ideal for dense urban engineering, cadastral surveys, and floodplain control. The downside is the cost and the upkeep. You know, field crews need to remeasure and maintain thousands potentially of physical benchmarks that can move or be destroyed or subside. And over long distances, the accumulated errors grow with the square root of the distance. So the network may need stabilization with other sources, multiple tide gauges. And you know it might need readjusting every decade or so, meaning that you might have new realizations of the same heights on the same benchmarks. The second option is the kind of the pure geoid model or GNSS based datum. So here the reference is a gravimetric geoid or quasi-geoid model derived from gravity data and terrain data. With no reliance on tide gauges, a single GNSS observation plus a geoid kind of interpolation gives us an absolute height anywhere in the country in seconds. And that's really invaluable for large, sparsely surveyed area, disaster response, and any workflow that really relies on GNSS. Routine maintenance is also very minimal because the surface is mathematical and only kind of model updates are required. And yeah, I guess the drawback is that accuracy is limited to both the quality of the model and the GNSS observation. And even with state-of-the-art data, gravity data and GNSS, we're talking about 3 centimeters plus another 2 for the GNSS. So yeah, you're looking at 3 to 5 centimeters accuracy for those absolute heights. But that's often more than good enough for engineering projects, but not necessarily for kind of millimeter scale deformation monitoring. The third is the kind of the hybrid datum. So yeah, I think of this as maybe the best of both worlds, leveling continuity with the kind of modern GNSS on-ramp. We can stabilize legacy leveling networks by adding loosely constrained GNSS plus geoid heights at strategic points, or we can warp the geoid with a geometric layer so that it honors kind of key benchmarks or local mean sea level 0 values. The hybrid solutions suppress long wavelengths in the leveling data and reduce the need for expensive re-leveling over hundreds of kilometers, and let GNSS users kind of slot right into the existing framework. The trade-off is that we kind of knowingly introduce potentially controlled distortions into the geoid surface so that the datum's no longer a pure gravity equipotential surface. And we still have to look after the kind of the main benchmark skeleton. So we're still maintaining a leveling network with this approach. I guess, yeah, longevity sort of sits between the other two options. It's better than a purely leveled network, but it's still kind of tied to that physical benchmark infrastructure. So yeah, in short, my recommendation would be to use a leveling only datum where sub-centimeter precision over short baselines is critical, and you already have a dense benchmark kind of infrastructure. Use a geoid model for nationwide low maintenance access to heights with GNSS, particularly in remote or tectonically active regions, or adopt a hybrid approach where you need to protect decades of leveling investment, yet kind of bring your jurisdiction into the kind of the GNSS era, accepting kind of small but very well characterized biases and distortions as the kind of the price of that compatibility. So yeah, the next few slides I've got here really just give an overview of the process to compute a regional scale geoid model. We're going to touch on the data that goes into it and very lightly on some of the computational steps. It's very mathematical, and I've really tried to step back from the equations and just provide an overview of the data that's going in. But if anybody would like more detail, I'm very happy to provide it. So yeah, before we crunch a single number, we need to sort of make some decisions. So the first is kind of which surface would we like to produce? So the classic approach is to produce a geoid model, a pure geoid model, which is very much suited to modeling water flow, but it does need technically, if we're not going to make any assumptions through the kind of the modeling process, we need a 3D density model. And that's used to convert the gravity data into the geoid model precisely. The other option is a quasi-geoid that kind of sidesteps that density guess that we need. But it comes at the cost of kind of typically centimeter level differences. But that's kind of well within the uncertainty of most of these models anyway, and in my opinion, forgivable. So yeah, we use a quasi-geoid model in Australia, and I guess today I'm really going to be focusing on that simpler kind of computational process. And I'm not really drilled into the nuances beyond that. The second decision we need to make is how big is the sandbox? The gravity field you kind of have at any point is influenced by mass density distributions from kilometers away. And so we need to understand how big our computational area is before we start doing any calculations. There is a process that we employ called the remove compute restore process, and it needs a buffering. So if we're going to use a very long wavelength reference model through that process, which provides stability to the long wavelengths in the model, we need to ensure that the spectral content is kind of accounted for. So, for example, if we wanted to use a satellite only gravity model, which might only have wavelengths up to 300 kilometers, we need to pad our computational region by at least that much. Ideally, maybe 2 or 3 times that wavelength to ensure that we don't have any kind of edge effects creeping into the geoid model where it counts and where we need it. The third decision, in my opinion, that we need to make is what resolution do we want the model at? So 1 arc minute is kind of the typical standard. It keeps the files quite small and the computations kind of sensible. We're able to run them on typically desktop computers or, low cost infrastructure. Finer scale grids do look attractive, but the benefit really is only at that millimeter level. Again, far below that kind of 2 centimeter accuracy level that we'd really expect from the geoid model. The third decision is, what is R0? I mentioned at the start that these models are often aligned with the global ellipsoid, but we could also align it with anything else, like a tide gauge observation, by just shifting the model by a constant value. And this is maybe the first step really to creating a hybrid model, as we described earlier. But these decisions, once we've locked them in, they kind of define really the purpose, accuracy, and in some ways the longevity of the model. And if we get them right, everything else downstream just becomes almost mechanical. Change. There we go. Okay. So yeah, there's really 4 data components to a geoid model. The first is high resolution gravimetry coverage, the choice of a global gravity model, which we use as a reference, a reliable digital elevation model, and some independent data to do some assessments. So the idea with the gravimetry is that we aim to grid up the gravity anomaly field at the same resolution as the geoid model. So ideally, we need this data at or finer than the kind of the target geoid resolution. So better than 2 kilometer spacing. We're aiming for 1 arc minute. Every survey, whether ground, airborne, or marine, should ideally be leveled to an absolute gravity datum. So that can be established with A10 observations or FG5 measurements. One of those absolute gravimeters that we saw earlier. And offshore, we typically tend to fill the gaps with satellite altimetry data and shipborne data that kind of ensure that the modeling doesn't break down around the coastal zone. Airborne data are probably the preferable method to have complete continuity between the onshore and offshore areas, but satellite altimetry fills the gaps reasonably well. So yeah, the global gravity model provides that kind of long wavelength reference for the modeling. We typically only produce a geoid model over a defined area, but formally the model itself needs gravity data to have global coverage. The trick that we play is to do this thing called the remove compute restore process, and we subtract a long wavelength model from our gravity data, compute the high frequency geoid model component, and then add it back at the end. So we sidestep that issue altogether. There are many global gravity models available, and they're available via that link there. Some of them have terrestrial gravity data that have gone into them. Personally, I prefer to use a satellite-only model because it retains that kind of independence between the data sets going in and gives you better handle on the kind of the uncertainties at the end. Although that said, the current generation of the model we use in Australia is based on EGM 2008, which does indeed have the kind of terrestrial data in. We also need a reasonably reliable digital elevation model, and this is doing 2 jobs. It's used to kind of compensate for topographic effects. We need to adjust for topographic effects so that the gravity data can be kind of appropriately processed and become harmonic, so that the conversion between anomalies and potential is kind of reasonable. The second job that it's doing is providing kind of 3D grid nodes for the gravity data interpolation. And that fourth data set. So if we have independent points where we've observed a mean sea level height with leveling methods, but also GNSS, we can kind of determine a geometric geoid value just by taking the difference. And they just provide that sanity check. So when you have your geoid model, you can compare it to those data sets at the end and have a kind of external kind of idea of how well your modeling is performed. Although that can be wrought with issues, and I've got a couple of examples of that. So yeah, the first step is really around kind of stitching all of your gravity data together. So we take satellite altimetry derived anomalies offshore. I'm quite keen on the DTU and the Samuel and Smith versions of the models because both come with their own uncertainty estimates, which can kind of support some of that data blending, particularly in the coastal zones where those data are slightly less reliable. We have airborne gravity data over the land and coastal zones, and shipborne data and terrestrial gravity data sets. And at every overlap, we can do things like check for biases and just ensure that the kind of the seams are minimized and disappear between the data sets. Yeah, and it's also ideal to make sure that all of these various data sets are referencing the same gravity datum, so they're aligned as best as possible going in. The target product is really a regular grid of gravity anomalies, reference the Earth's topographic surface as defined by our digital elevation model. And an example grid of gridded up gravity anomalies is shown there on the right. We kind of have seamless grid of data from altimetry derived anomalies and the terrestrial onshore. And future versions of this map are going to include some airborne gravity data sets that have been collected over Victoria, New South Wales, and a targeted region over South Australia. Yeah. So yeah, the kind of the process of including that airborne data is going to complicate things a little bit. We're going to need to simultaneously bring those gravity data down because they're not measured at the topographic surface, but there are kind of various ways to do this, one of which is called least squares collocation. And this is an incredibly powerful technique that lets you kind of blend gravity data, consider the errors, and do the downward continuation at the same time. It gives us kind of a bit more rigor than just simply gridding up the data with splines. So yeah, the gravity field itself at the topographic surface is not technically harmonic. And in essence, really what this means is that the data themselves don't directly play very nicely with the equations that transforms a gravity anomaly into a disturbing potential. So we have to apply some corrections to account for this. You can imagine a scenario where you're at the foot of a mountain and the mass of the mountain is pulling upwards. And so your gravity data are technically lower than what they should be if they were above that mass. So the calculations themselves to go from an anomaly to the disturbing potential assumes that all of the gravitating masses are beneath the calculation point. So we have to apply some kind of correction to account for this. The very simple approach, and one that we've used in Australia for the last few generations of the model, is to apply what's known as the topographic terrain correction. And this kind of smooths the gravity field out and replaces the gravitational effect of topography with just a flat slab. And it kind of simplifies the process with kind of minimal kind of errors introduced. So yeah, on the left there, we've got the gravity anomaly as kind of derived from just the raw data, and then on the right is that effect from the topography. So you can see it's almost, yeah, maybe a sixth of the signal. Yeah. So I've mentioned it already, but the next step is the kind of the so-called remove step. So we actually used EGM 2008 in the last modeling process, and that has terrestrial gravity data that have gone into it from the same database that we're using here. So we take EGM 2008, compute a gravity anomaly, and subtract it from our gridded gravity anomaly data. And yeah, it kind of provides that long wavelength support to the modeling process. And in doing so, it kind of strips out any kind of long wavelengths temporarily. So we've gone from about 30 milligauss standard deviation down to about 3. So it's really reduced the size of the signal. So the next step is to transform our residual gravity anomaly into a kind of a residual quasi-geoid. The classic route to do this is using Stokes integral, where we convolve the residual gravity anomaly with Stokes kernel to kind of recover that kind of corresponding geoid signal in the spectral band that we've kept. It sounds complicated, but there are software packages available that can do this, and I'm happy to refer people in the room to those. There are other approaches to do this too. We can actually use least squares collocation directly. It's not just a gridding tool. We can do those transformations with that framework too. It kind of performs the same physics, but it lets you weight the data and also estimate uncertainties too through the process. There are also other kind of fast Fourier transform based convolutions, some that use tapered or adjusted kernels for controlling the spectrum of the derived geoid anomalies, or other approaches like Hotine's integral, which can do very similar things, provided the anomalies are being calculated the right way. But regardless of the kind of the flavor of the approach here, the objective's the same. We're trying to convert short wavelength gravity anomalies into short wavelength geoid undulations. So you can see here that we've produced from our kind of high resolution, high frequency map of gravity anomalies. We've turned that into geoid undulations with a standard deviation of around 3 centimeters. So very small changes. Do the thing. So yeah, the final step is the restore step, which is really putting that long wavelength information back in. We take our high resolution residual geoid surface we just computed and simply just add back the EGM 2000 here anyway, the EGM 2008 geoid undulations that we removed at the start. So this is kind of reinserting all degrees, medium, long, and short into a kind of a single seamless model. And yeah, the result is the geoid or quasi-geoid that kind of carries that trusted long wavelength information from EGM 2008, as well as our local gravity data's fine detail. So yeah, ready to go for a GNSS heights kind of application. Okay, so as a kind of a final step, we need to check the model. And we do that by using that independent GNSS minus leveled heights data. So these points give us discrete points where we can calculate the geoid to ellipsoidal separation and yeah, evaluate the accuracy of the geoid modeling. And often the comparison is used to fine tune our geoid modeling process. We might use this in an iterative fashion where we do some manipulations to the way the geoid is calculated. But yeah, effectively, it's just being used as a check. These comparisons are difficult though, and often wrought with difficulty. So we've got here an example of the difference between the kind of the gravimetric geoid model and GNSS minus leveling derived heights in Australia. And there's a significant north-south trend and a fair amount of variability. So really, the best we can say from this comparison is that the modeling was accurate to around 18 centimeters. It's basically tying back to that issue that I mentioned earlier of the mean sea surface being used to establish AHD. It's embedded deeply within the AHD, the Australian height datum, the leveled heights, and it causes a great deal of difficulty when we come to do these comparisons. So just to dive a bit deeper into this, I've got a few slides on the Australian context. So yeah, the Australian height datum is the officially kind of legally recognized height datum in Australia, and it's been that way for more than 50 years. The datum itself is based on thousands of kilometers of primary leveling, shown as the kind of the thick black lines in the figure on the left. And it was anchored to mean sea level, determined at around 30 tide gauges around the coast, which are numbered in that figure. There are kind of ongoing efforts to maintain the physical infrastructure, but warps and distortions are often evident in the datum due to things like ground surface motion. And the key issue when we consider its compatibility with a geoid model-based datum is the kind of that deeply embedded sea surface topography that I mentioned. The sea surface varies significantly relative to the geoid around the Australian coastline. It's offset by nearly 1 meter in the north, down to about 0.2 meters in the south. And this is the kind of the predominant source of those errors that we just saw. mean, it's great for local accuracy near tide gauges where we want to reference sea level, but it kind of forces the network to be warped on the whole across the continent. And it makes it a little bit impractical for kind of large scale use, like digital elevation models, which can be kind of used for those broad scale water flow modeling. Not to mention it's only really formally defined at those very discrete points. So yeah, in some ways today, the Australian height datum is a bit of a hybrid datum in that we provide access to the datum at benchmarks for leveling derived heights. But we've also produced a kind of an accompanying geoid model, which has been warped to fit the Australian height datum leveled heights and me sea level, kind of as realized in the 1960s when the datum was established. And we do this so that GNSS users can get AHD heights too. So we grid up and effectively add in an extra layer to the gravimetric geoid model, which captures those differences that we get when we compare the GNSS leveled derived kind of geometric heights to the gravimetric model. And we call this, or at least the current generation of this model, AusGeoid 2020. So yeah, it's worth keeping in mind that this surface not only accounts for mean sea surface embedded in the datum, but all of the kind of the bumps and wiggles in the data due to things like gross leveling errors or marked movement between the time when the leveled heights were established and when they were GPSed. Yeah, so we're really kind of forcing it to fit that existing leveling infrastructure, for better or worse. Effectively, yeah, it's deliberately including errors to ensure users can access AHD heights via GNSS as if they were kind of connecting to leveled benchmarks. And formally, it's only really defined on those benchmarks. So yeah, it's all well and good for applications that specifically require AHD heights, where legislation dictates heights must be provided as AHD. But I guess in many ways it's kind of detrimental to applications that need more rigor and scientific kind of sound heighting. So yeah, all of those use cases mentioned earlier. It also means that we have no way of connecting onshore datums and offshore datums for things like under keel clearance and ships navigating in and out of ports when using AHD. So for this reason, in 2008, we've been kind of promoting the use of an alternative datum level, which we refer to as the Australian Vertical Working Surface, or AVWS. And this is kind of a gravity only geoid model based datum, which is aligned with the mean field of GRS 80 using a properly defined 0 degree term, and it's seamless on and offshore. Yeah, it's kind of, the idea is that it's meant to be future proof compared to AHD, and there's no physical infrastructure, at least once the model's been computed. So for the throughout that kind of modeling process, we also computed some uncertainties, and we did this via error propagation of the raw source data. So through this process, we found that not only is AVWS more theoretically rigorous, but all signs also point to it having a lower uncertainty. The AusGeoid 2020 uncertainty sits at around 10 to 15 centimeters. It's worse where the GNSS leveling data thin out and we can't properly estimate it, particularly through the center of the country, which leads to the datum being kind of poorly defined. But meanwhile, the uncertainty in the gravimetric only geoid model is generally below that 5 centimeter level. It does climb through in regions of rough topography where the gravity data coverage is a little bit thinning out and not quite having the density that it needs to capture the full signal very well. And a little bit in coastal areas where it's kind of heavily influenced by altimetry derived gravity data. But it's generally speaking better than AusGeoid 2020 in terms of that pure uncertainty. And I'll note here that this is a big factor in how we sell the model to the user community. Being able to kind of articulate the benefit of an adopted lower uncertainty AVWS model is really quite a powerful thing to be able to say, and it's kind of helped with uptake. So I'd recommend that anybody kind of embarking on this journey of computing a geoid model also considers doing corresponding uncertainty estimates too, particularly if you're trying to transition away from a leveling datum towards a geoid model based datum. So yeah, I mentioned earlier that when it comes to establishing a height datum, you first need to make a choice between a leveling-based datum and a geoid-based datum, or some kind of hybrid. So in many ways, Australia, we have all three. The lay of the land is really kind of as follows. We have AHD for leveling only, high precision work with legally recognized heights. And then jumping to the bottom of the table there, we have a hybrid AHD with those Geoid 2020. When GNSS data are used for rapid heighting, but we also need to tie back to that historic datum. So albeit with less precision than just using leveling data. This is perhaps kind of more applicable to subsidence monitoring with kind of local high water levels referenced to AHD specifically. And then the third new option, the so-called Australian vertical working surface, with is really ideally used with GNSS for kind of efficiency. It's uniform on and offshore, and it also provides that kind of scientific rigor where that needs to take priority. Having lots of options is great, but I will note that it comes with overhead. It means that we have to be able to communicate this effectively and be able to describe which surface projects might need and why, and help users make the right decisions about which one to use in the particular scenario. So yeah, I think taking this route really does require providing a lot of support and documentation just to ensure that it's implemented and used effectively. I'm just going to finish with a brief case study. So this is around a project that's underway in the state of Victoria, where we have been trying to densify the existing gravity data coverage to improve the gravimetric model. So to set the scene for how this project came together, 3 project partners really kind of rallied around a shared vision to improve GPS-based heighting across Victoria, but also to enhance existing gravity holdings for the exploration sector. And we did this by, they do this by releasing pre-competitive gravity data for regional scale geological assessments. So the 3 groups that got together were the Land Use Victoria's Geodesy branch, who took the lead on funding the funding brief and spelled out the height datum upgrades and why we needed to do this. The second party was the Geological Survey of Victoria, which saw the kind of the exploration upside, put up co-funding and supported the extra coverage in the Eastern Highlands. And then Geoscience Australia, who kind of supplied the airborne gravimetry know-how and led the project and kind of played a bit of a coordinator role. So yeah, from there, we built a 2-part business case. Part 1 was the geodetic part, where we used new airborne gravity data to reduce the quasi-geoid uncertainty down from a roughly sort of 5 centimeter, 8 centimeter level down to about 2 to 3 centimeters across that survey area, which includes kind of urban areas where good heighting is really critical. And part 2 was that kind of geoeconomic angle where we would publish high resolution data openly so that explorers and groundwater modelers and hazard analysis people can have access to the best possible gravity data for their work. So yeah, there was a combined value proposition for both the state and the Commonwealth, which drove a funding agreement under a national collaborative framework. And once the dollars were signed off, we hit go on the whole thing. So yeah, in summary, we had 1 vision, 3 project partners, and two deliverables, and a green light from all of the relevant financial delegates. So yeah, it's probably worth noting at this stage that none of the 3 participating agencies have, with the other 2 particularly, well, all of us in fact don't really have any individual airborne gravimetry capabilities. We had to outsource that. So next came the approach to market. We put out an open request for tender, which we drafted jointly by between us, with specs that included 500 to 1 kilometer flight line spacings over our area of interest, the lowest possible ground clearance, which sits within public airspace, as well as a number of requirements around the type and accuracy of the instruments that were going to be used. We also had requirements around the supplier passing an air safety audit and CASA compliance to just ensure that those operations were as safe as possible. Airborne geophysical surveying is incredibly dangerous and things can go wrong. So you really do need to get your ducks in a row to make sure that you're covering as much of that off early on as possible. There are a number of airborne gravimetry vendors operating internationally, and we received quotes from 4 of them. And we evaluated the responses based on the suitability of the systems they proposed, preferring scalar airborne gravimetry systems with kind of 1 milligauss accuracy and able to capture around 4 kilometer wavelengths in the gravity field to match that 1 arc minute spacing in the model. And we also took into account the supplier aircraft availability within respect to the kind of the project deliverables and critically whether or not those quotes represented value for money. So that's really how we pieced it together. There we go. So Sander Geophysics or SGL offered the best technical score and value through the tendering process, and we offered them the contract for the data collection. The quote was for nearly 200,000 line kilometers, covering the survey area shown there on the right, with north-south primary lines and east-west tie lines every 20 kilometers, which are used to kind of check the accuracy of the data at intersection points and to kind of facilitate any re-leveling of the data to make sure we got a internally consistent data set. So Sander flew this area with their airgraph system on board the plane, which is a scalar gravimeter that kind of met our accuracy requirements. And yeah, they flew it in a dual propeller plane, which is shown there on the left. And this is a kind of aircraft type that is really important from a safety standpoint due to the course topography and the large offshore component, because it offers that kind of long endurance, meaning they typically were able to get back to a safe landing spot, but also had the ability to fly several hundred line kilometers of data per day. The data collections are a little bit weather dependent, and the gravimetry systems perform best really in nice, smooth flying conditions to capture the best data. Yeah, at the end of the day, the gravimeters are a big kind of accurate accelerometer. So turbulent flight conditions can significantly degrade the quality of the final data. And yeah, weather delays are a fairly large consideration in these surveys. So data collection can be a little bit stop-start with this kind of thing. We wrapped up the survey in October last year, capping a campaign that began back in March 2022. And the coverage was also changed a little throughout the survey to eat up underspend and ultimately stretch from Cape Crossing to the metropolitan Melbourne and climbing right over the Australian Alps. Exactly the kind of the rugged, hard to reach terrain where ground gravity has always been a bit patchy and thin on the ground. Over the Alps, we can see the gravity signal is strongest, which is kind of sandwiched between Wodonga and Barnsdale, and flatter elsewhere where the kind of topography is less coarse. So really, we are capturing those mixed density variations beneath the aircraft. Importantly, we also went about 50 kilometers offshore along the entire coastline. There is a gap there in the middle, you probably picked up, but that's actually been patched already with a previous survey that was done for, I believe, oil and gas exploration. It's really trying to cover those areas where we would have otherwise had to have used altimetry data. And it's notoriously kind of unreliable in the nearshore zone just because of sea surface topography. And variations due to like tides and other aspects that kind of make doing altimetry and gravity derived altimetry data difficult near the shore. And it's greatly improved the gravity data coverage. The data is still being post-processed right now and quality controlled. But once this processing is complete, we're going to release them in the coming months through the GA data portal, which is noted there in the footer of the slide. So just to show a couple of very preliminary results, On the left there, you can see the residual geoid model over Victoria, where we have these data. Here we've used the long wavelength model from the Gaucher satellite only data. So it's approximately about 150 kilometers wavelengths as that reference signal in the remove compute restore process. And you can see relatively kind of fine scale structures with a total range of about 0.5 meter. Giving us, well, plus or minus 0.5 meter. So we have about, 1 meter peak to peak variations in the residual geoid surface. On the right, we've actually processed the data and produced the model using least squares collocation. So we've also managed to capture the uncertainty estimates. And we're kind of smoothing out the uncertainty across the entire region. So it's uniform, whereas before it would have been a little bit more variable due to the variability in the data coverage. Overall, we're kind of approaching that target 2 centimeter level in the raw error propagation, and some comparisons to very high quality GNSS and leveling derived heights are reflecting much the same. I think it's important to note that these are kind of preliminary results, and things may change with the final data product. And I think that kind of concludes things really. That's the end of my talk. So thanks very much for your attention, and I welcome any questions.
Thank you, Jack. Great summary of a lot of hard work that you've done over a number of years, and to summarize that in just over an hour, I think is very impressive. So thank you. I feel like I need to go back and I'll watch the recording myself to get re-listen to it. And that's the advantage of the recording. You can go back. Often Jack has to tell me things and I need to write it down and read it 5 times and then I understand it. So if you need to go back and listen, don't feel ashamed, because that's what I often have to do. So thank you. It's almost a masterclass. I feel like we could get you on those masterclass series, how to produce a geoid model for your country. I'm sure there are some questions and there may not be enough time to cover them all now, but let's get started. So who wants to go first? Yes, please. Thanks.
Okay, thank you, Jack, for the presentation. I'm Bagas from Indonesia. Actually, based on your presentation, first, the Indonesia has released the National Geoid Model of Indonesia, as known as the UN-GGCE 2020. Since 2020, it generated from the combination of the terrestrial, airborne, and several for the DTU-17 from Denmark for the marine area. My question is to first, we would like to know your suggestion or maybe your opinion is how we can joining the land and marine data, because we would like to propose the UN-GGCE, the geoid model, to be the single reference system for the vertical value. But for sometimes, for a reason, in Indonesia, it's quite challenging due to of the oceanographic condition and also the difference of the chart datum for each island. And then the second one, that in Indonesia, we are realizing for the geoid vertical datum, it means that we would like to apply the GNSS heightings, how we can quantify for the vertical accuracy for each point, because as you know that in Indonesia, we estimate the accuracy of the UN-GGCE model is by the GNSS leveling for some validation points in some region of Indonesia. Thank you, Jack.
So I think generally speaking, if you're looking to blend data sets, least squares collocation is the way to go, because you can combine different sources of data and use their respective uncertainties, or at least what you know of the data to optimally blend them. If you have multiple geoid models that you're trying to bring together, looking for offsets between them would probably be the first port of call, or subtracting kind of linear trends from them to make sure that they fit nicely together. Forgive me if that wasn't quite what you meant there, but perhaps we can catch up afterwards and discuss that in a bit more detail. With the uncertainty estimates, you're right, using GNSS and level derived heights, as I showed there, even in a country like Australia with quite a well-defined leveling datum, it can be problematic. Uncertainty propagation using a method like least squares collocation, or pushing the uncertainties of the data through Stokes equation or the other kind of calculation methods is another good way to get a bit of a handle on how well the modeling has gone and the quality of the geoid model.
Thank you. Great questions. Anyone else? Richard.
It was a really great presentation, Jack. The best summary of geoid modelling I've come across, I think. Good. This is a question that probably can't be answered, but it's one of those things that's a bit of an annoyance. Is the obviously a gravimetric geoid is really important for large-scale hydrology studies. I mean, you can't really get around that. But the issue is, how do you actually relate that with mean sea level, which is obviously when you're looking at the interaction of the land and the sea. You obviously have a land-based hydrology model for drainage and flooding from land-based hydrology, but then you're trying to merge that with the impact of the sea. You have a bit of a conflict. That you have your sea level surface, MSL, HAT, LAT, and you're trying to integrate those two together. It makes it really hard. I don't know if you can answer that, but
I think I might pass that question to the gentleman who'll be talking next. I think he's going to be covering a topic very similarly, but it's it's a similar problem to what we have with those comparisons to AHD derived level heights. They don't play nicely with one another. Locally you can apply offsets to make sure that the region you're working in a very close zone is compatible. But generally speaking, I think there's more sophisticated approaches that need to be taken, and hopefully we'll hear a bit more about that in the coming talk.
I have to tell you upfront, we're not looking at tidal datums, so I may not be able to. But I think that Cornelis, who is the gentleman after me, should be able to say that.
This is called it's the 10:20 past the buck time. Yeah. Overall though, Richard, you're asking exactly the right question, and one of the objectives we have in the centre is to try and help address that question. So it's really and what Avert's going to be explaining to us is the key role that the geoid plays in being able to integrate these data sets or align these data sets. But there's not a simple way to do it. And so you can use the geoid as that physically meaningful surface, which is onshore and offshore. That becomes your connection to align your data sets onshore and offshore, but you need different models to get to the geoid. And it's about understanding the uncertainty of the different data sets onshore and offshore. And then you connect that to the geoid, and then you'd use the geoid to connect back to your land. So Avert's going to be talking us through how we do that from the perspective of the land base to connect to the geoid. And then Cornelis is going to be talking about how to connect from the ocean side to the geoid. And then you'll have both sets to link these bits together. So we understand how to do it from the land side, but we need people from the maritime side, like Cornelis, who's going to join us to explain how to develop those models from the maritime side.
Yeah, that's really good. Excellent. Just perhaps a quick question. What's the status of the current global geoid development? Is there a new geoid coming out?
There are satellite-only models released very regularly. In fact, the GRACE data, the follow-on mission, those long wavelength models are frequently updated. I'm not sure where the production of the next generation of EGM kind of modeling is at right now. I think just keeping your eyes peeled on that ICGEM website and watching the release is probably the best I can say on that.
Yeah, thank you for your presentation, Jack. I want to ask about the Australian Hague datum using 30 tidal gauge that in your calculation, but you already have 38 tidal datum, right? So what's your consideration that didn't use the other 8 station? So, and then the second question is, what is your main consideration to install the specific location of the tidal gauge? Is there any plan to add more station of the tidal gauge? Thank you.
So I'm not aware of there being an additional set of tide gauge data that didn't go into HD. Perhaps you're more familiar than I am. Yeah.
So the tide gauge is the 30 around the Australian mainland. There was 2 in Tasmania. The 30 around the Australian mainland came from data in the late 1960s through to early 1970s. And the 2 in Tasmania collected data in the early 80s. So there might be more now, but at the time, they were the ones that were considered as being accurate enough to feed into the observations.
Oh, yeah. Is there any plan to you to add a more station to the coastline of Australia? Delegate station.
No, I don't believe there are plans to do that at the moment. Right now, we're encouraging users to try and transition to the gravimetric solution where they can, where they don't need that kind of tie back to the legacy datum. But AHD is very much fixed, and I don't believe there are plans to update the leveling derived heights right now.
Thank you.
I'll come back to you in a minute. We've just got a question online. Viliami, are you able to open up your mic if you wanted to ask a question?
Yes. Thank you, Nick. Can you hear me?
Yeah, go ahead. Thanks, Vili.
Okay. Good afternoon, all, and it's good to join in the workshop. My apologies for a colleague from Tonga who is unable to be with you guys during the workshop, but it's good we can join in online. Just first of all, thank you for the great presentation that we just seen. As you all know, that is one of the critical issues with islands in the Pacific, to have a modern height system. I think the current height system in the region is not that relevant to things are now. So it's good to see the presentation in Australia that, for me, first of all, everything can be done. So we can see the example from Australia. What I wanted to see is how we can scale down the experience in Australia to a smaller island states. We have seen the development of different surfaces, different height system. For us in the islands, maybe more simple than Australia as a big country. But I would love to see what are the best options for us in the Pacific in developing a modern high state system for us in the Pacific. We have tide gauges, we have GNSS stations, but we're still missing something. We are still trying to work on it, but it would be good if the experience from Australia, how it can be scaled down to small islands so they can develop their height system. Thank you, Nick.
Yeah, it's a great question. Thanks, Viliami. It's something that Andrik and I have talked a bit about, and I think particularly in his new role, there's an opportunity now through PGSC to be starting to develop some business cases which could go through get from aid funding, and it could be for things like collecting terrestrial gravity observations, potentially airborne gravity if there was enough support from aid agencies. But if you collected the right amount of data and had that information available, you then have the expertise to capture the GPS leveling data, which is used to verify the geoid model. So that would be a role that you can already play in your countries. But if you were able to get support through aid agencies, and we could work with you on the development of a proposal through PGSC to collect the gravity data that's required, I think you would then have most of the work done to in order enable you to develop an improved height system and geoid model in the country. So let's talk about that with the PGSC and Andrik. I think that would be a good way forward.
Yeah, thank you, Nick.
Great question. Thanks. And Ava, you had a question.
Yes, thank you, Nick. Thanks, Jack. That was a very great presentation. And I don't know if you already had a look at the paper. But you would see, and later we will all see that there's quite some matches between what you have presented and what we have in the paper. Your presentation was way more elaborate, so I'll be referring to that to build up my paper. But a question that I have is like, so in Singapore we have we call it a geoid model. It's actually a separation model. We realized. However, it does provide us with 3 to 5 cm accuracy. And just now you mentioned that that is kind of the accuracy that you would expect from a good geoid model. And we are actually working on towards developing a gravimetric geoid. And we will still continue that. But my question more is, if the 3 to 5 cm accuracy is all that we can get, would there really be a reason to do so?
A great question. Yeah, I think part of the problem here is verifying that accuracy. You end up being limited by the leveling data, which are tied back to sea level, it's some tide gauge, plus the GNSS observations. It becomes a game of how do you verify that? It's a tricky one to try and unpick. You can probably do get down to a 2 centimeter level geoid model, possibly better, but when it comes to proving that, you've got your work cut out for you. I think that's really where the key challenge lies there. But I think it's worth attaining, kind of aspiring to. Yeah, the more gravity data, the better quality that is, the closer you'll get. Yeah.
Thank you.
Is the current accuracy you can achieve, which sounds quite good, is that because you have a very good leveling network throughout Singapore? Is that the reason?
We have a fairly good network across Singapore. I do not know what is the criteria of saying it's good or. I mean, the network is dense, a lot of points, and they are close to each other. Yeah. And just a follow-up question, if I may. So there is a lot of standards in terms of GNSS observation for 2 dimension. But what is the standards of GNSS observation for third dimension in order to verify height? Because we don't really know what is the good standards, what kind of observation to achieve the accuracy that we are talking about.
It's a great question. So particularly for the verification part, the recommendation is that you get GPS leveling lines, and you want quite a long leveling line in different sections where you're trying to evaluate the geoid. So I know when we were doing the work with talking with South Australia and Victoria, there was a lot of discussions around getting different lines to verify the quality of your geoid modeling in different regions. So ideally, you'd want to, in particular to the GNSS component, I think you'd want to pick an area to collect data and do some sort of campaign observation. So you probably want to collect about a week's worth of data. And that should allow you, with dual frequency processing, to get you down to sort of 3 centimeters in height. And I think that with the leveling data is then going to allow you to verify the quality of any airborne or terrestrial gravity that you capture through that region.
Thanks, Nick. Thanks, Jack, for a great presentation. It was really insightful because we do have data, but in the Pacific, GNSS data and leveling data. Unfortunately, we don't have a geoid model for the Pacific. I mean, we are, I think, looking forward to, like what Nick said, collaborating with our partners at NGS to at least go for the airborne gravity. Hopefully, we can strike through that too as well, and get some donor agencies to actually support that. So that's what we are looking at. My question is that we do have, as part of the Pacific Sea Level Geodetic Monitoring Project, we do have sites which we have like GNSS pillar, leveling data, and the tide gauge stations. With that, if you see that, for example, Tuvalu has 9 atolls, and the tide gauge station and the GNSS core station is in Funafuti. And if you have that instrumentation and infrastructure there, can that data set can be used to develop a geoid model for the whole of Tuvalu? Because I've seen actually someone doing that. Yeah. But never, we didn't have any geoid data.
With that kind of infrastructure in place, what you can do is lean on an existing global model.
Yes.
So you could take something like EGM 2008,
Yes.
cookie cut, and then align with existing infrastructure. So if you have tide gauge observations, then you could effectively apply an offset to make it agree as best as possible with what you've got. And that would probably be my recommended approach, where there's no extra gravity data.
Yeah. We can do that in Funafuti. That's my understanding, is that we use the geoid model, the global geoid model, 2008. But my question was that can we do it for whole of Tuvalu, which has 9 atolls, and the islands are separated by hundreds of kilometers, and atolls actually. Yes, thank you.
Provided the mean dynamic topography, that kind of sea surface variability that's not related to the geoid, is quite flat, I think it would work quite well. I think it'd really have to be a case of looking at the data and seeing how they sit relative to the model. Yeah.
Thank you. I think that answers my question.
Yeah, did you say that you've seen this done by somebody already?
Yeah.
If you can share that with us, I'd be interested to see it, and then Jack and I can have a chat about whether or not we can turn that into some sort of guidance document that's available to people to explain what that means, how good it would be, and what you could use it for. I think that would be useful. So if you can share that with me, Hendrik, that'd be great.
Yeah, so we do that in the islands. Is like when we do the LiDAR surveys, we deploy the tide gauge stations, and we get the tide data, and we establish the mean sea levels. And then how we are able to do is translate that, using GNSS. And then again, we do transects as well to calibrate the LiDAR data. All of that is done. But then again, we need to verify that LiDAR is correctly, auto-rectified, to the actual vertical datum. And that's what we saw. But then that's where we see that, okay, but there's some islands and atolls are different. And it's changing heights as well. It's like rugged as well. So it's like what, Jack has mentioned.
Yeah,
like in islands and atolls which are flat, but some islands and atolls are not like that. So it can be used nationally, or can be just used on one island atoll as well.
Thanks. Now, I know I'm into your coffee break. I'm making a very deliberate reason for that, because I don't want to fall behind time, but I also want to make sure, so I can't push this into the next session, but I also want to make sure you get to ask Jack your question. So happy to take one more, and then we'll have a 20-minute break. Yes, thank you. Sorry, Mahesh, we'll come to you next.
Okay, for the country like the Philippines with several islands, if we fix the leveling network to one tide gauge per island, do we need to fit the geoid to every tide gauges also?
It's a good question and a very difficult scenario to navigate. I think when it comes to evaluating the quality of the model, you'd probably be best off removing a bias from each individual, so suppose kind of local vertical datum that's established by referencing an individual tide gauge. Or perhaps you could look to use a mean dynamic topography model to remove those offsets for each individual tide gauge and try and bring things down to a uniform level to start with. If the tide gauge data are collected at similar epochs as well, you might find that there's more consistency than if the tide gauge zero was established at different points in time for different islands. There's a lot to unpick there, and I'd be happy to maybe talk a bit more over email.
I was even going to suggest, I think your situation, that's very complex. What I'd recommend is that we've got time Thursday afternoon and Friday morning on our roadmap documents. Maybe in one of those sessions, you could sit down with them for half an hour and understand what their requirements are and sort of map out some options. And that would be enough, I think, to get you started. So yeah, let's spend a bit of time doing that. I think that'd be valuable. Mahesh, last one. Thanks.
Thanks for the wonderful presentation. I'm more concerned about the gravity data, and when I try to find the amount of surface gravity data, there's not many, I think, papers indicating the density of data. But here I've seen in your presentation that you have mentioned the data should be less than 2 kilometers. So is there some kind of standard, or does it also depend upon the topography of the nation? And one more about the absolute gravity data. So in case of Nepal, we had one absolute gravity observation in around 1991, I guess. So how updated does it have to be? And how many stations do you think is necessary?
I forgot what the first question was, so I'll speak to the density.
Yeah.
So look, I think really being able to grid your data up at the same resolution model is an absolute ideal scenario. You can get away with a lot less. There are tricks you can play, so removing the effects of the topography and gridding up that field, and then restoring the effects from a digital elevation model that can mitigate topographic aliasing. It's very much an ideal scenario. I think working with what you've got probably first and seeing what the quality of the geoid model is probably the most pragmatic approach. Because yeah, as I say, there are ways around kind of perhaps having less data density than what you might be shooting for in an ideal scenario. When it comes to absolute data coverage, I think really the best practice is to have enough data to tie together disparate surveys. So, if you're in a situation like Australia where the gravity data are being collected at different epochs by different companies, you need a way to knit that information together. And that's what the absolute data does for you. If you were to say instead cover the entire country with a single blanket survey, you could probably get away with having no absolute marks and leveling up the airborne data in an internal sense just once, and then just taking a bias away. So yeah, it's not a restriction. I would really say that it's on a kind of a situation dependent basis. Having one absolute mark is fantastic to just be able to reference surveys to. So yeah, if you have one already, I think that's probably okay. Yeah.
Yeah, but I think it's done in 1991. So should we think of updating, or is it good enough?
I don't think it will have changed very much. We had a campaign around Australia where we actually measure 15 sites annually, and we see very little change. So I suspect that might be the case for you too, as long as it's in a stable location. Yeah.
Thanks.
Only because you did this. Go for it.
I'm not expecting an answer, but this is a non-technical question. So the reason why we need to develop a good geoid model for the country, I think we need to go beyond just the GPS heighting, because GPS heighting is given, it's something that we need to do, but probably in Singapore's context, we need to go beyond. What are the good reasons for us to get a geoid model, or even for everyone else? It should go beyond just a GPS heighting.
I think it's for Singapore, it's joining land and sea. That's the argument you want to make. You want to make about safer navigation, improved port operations. A lot of that is linked with GPS, obviously, so you can natively do these things more effectively and efficiently. But it's also then going to help with natural hazard modeling and disaster mitigation, as well as things like construction is another big industry. And I would say the construction industry in Singapore in particular would be heavily reliant on having an improved geoid model to allow them to, because construction sites need to work on physical heighting, and they want to do that more efficiently in a more automated way. So they would be the major use cases that I would be thinking about for a Singapore business case. Digital twins, the other one. So Victoria and New South Wales, the work that Jack has been doing with those two regions, they develop very strong business cases dependent on digital twin in New South Wales, and in Victoria, it was linked and they got some of the money through working with the mining area. So in those countries where mining is important, that's another strong consideration to get funding for an improved geoid model. All right, we're going to break there. Please take a short 15-minute break, and I'm sure lots of people have other questions for Jack. As I said, we're going to have periods on Thursday and Friday when you're going to be working on your roadmaps. That'll be your time to try and get more time with him to talk about your specifics. So I'm sure you'll be happy to walk around and help with that. Please join me again in thanking Jack for a great presentation.